Great. Today, I'm very excited to have Fei Gao here to tell us about some uh, some interesting ways of getting insight into QCD and how the real world operates. Fei, whenever you're ready, please take it away.
Yeah. Okay. Thanks for the introduction, and also thanks for the opportunity of this seminar. So I would like to introduce you my study about the QCD phase structure and thermal properties based on functional QCD method. This method is actually just to combine two functional methods together in collaboration with Yang and Yuans. So I will briefly introduce you the background and also the framework of the functional QCD method. And the main results are the phase diagram of QCD at finite temperature and chemical potential. And then, also we compute the QCD thermal properties. With this thermal properties, we can then access to the more experimental side, like the heavy ion cladron, and also the cosmological side, the universe evolution. So QCD is a non-abelian gauge theory, describes the strong interaction between hadrons and quark gluon. So at large energy scale, it shows asymptotic free behavior. And at low energy scale, there are basically two important features: confinement and dynamical mass generation. So this phenomena are mainly because of two important properties of QCD. One is dynamic, non-perturbative dynamics. The other one is non-trivial topological structure of non-abelian gauge theory. So the dynamical mass generation is mainly about the non-perturbative dynamics. So the non-perturbative dynamics is usually related to strong coupling, but essentially the non-perturbative dynamics it means that beyond the perturbative solution, there is another non-perturbative, non-trivial solution. So this non-perturbative dynamics is also is usually related to some symmetry breaking. For example, the dynamical mass generation of quark is simply a dynamical chiral symmetry breaking. But for gluon mass generation, it's more complicated. So it actually does not really break the gauge symmetry or any explicit symmetry in the Lagrangian, because so this mass generation is related to some condensate, and this condensate is exactly the Yang-Mills Lagrangian. So any symmetry in the Lagrangian also keep this condensate invariance. So this is so very likely related to the topological order phase. And also the Polyakov loop computation shows that there's relation between dynamical gluon mass generation and the confinement mechanism. And then so and then other studies about the special features like the instance of the monopoles. The studies actually show the relation between this different feature configurations. So this also related the topology then to the dynamical gluon mass generation. So the key property of QCD is this running mass behavior. Here is a typical result from functional QCD method for quark and for gluon. So for example, at large momentum, the quark and gluon show asymptotic behavior. And then in infrared region, there will be a dynamical mass generation. This this running mass will directly lead to this QCD phase structure at finite temperature and chemical potential. So for example, for high temperature and all chemical potential just offers a large energy scale. So the QCD states will show asymptotic free behavior, which is the quark-gluon plasma. And then as the temperature and chemical potential decreases, it goes to the normal hadron gas phase. So between this, there will be a phase transition. And the theoretical studies generally believe that low chemical potential is a crossover, and that high chemical potential is a first order phase transition. And then there exists a critical endpoint. This QCD phase structure can directly map into generally two scenarios. One is the heavy ion clearance, and the other one is the universe evolution. Both of these processes cross QCD phase transition. So these two scenarios are very good place to study QCD, and then also the QCD theory will give some results for the experiments on these two scenarios. So the functional QCD method are actually so there are two methods here. One is Dyson-Schwinger equations, and the other one is functional renormalisation group approach. So DSE is basically the equation of motion of quantum field theory. And this functional renormalization group is based on Wilson's renormalization group idea. But they are both the master equations for the effective action and can be diagrammatically depicted as like here is because we here basically study the chiral phase transitions, the chiral symmetry thing. So our main equation is the quark propagator equation. So here the quark propagator DSE is this integral equation, and for FRG, so this is the quark propagator FRG, and so actually it's generally speaking it's a differential equation. So
may I ask a question here?
Yes.
So
please.
therefore, here you are essentially when you do the resumation, you have all the rainbow diagrams, right? So where you have one.
So if the vertex is bare, then it's called the rainbow ladder. Yes.
I see. So you imagine that the vertex has additional corrections here.
Yeah, sure. I will show you that actually. So in our new scheme, we actually found a better way to truncate this vertex by combining these two methods actually.
But in general, it's a resummation of some kernel that you assume for the Schwinger-Dyson equations. That is a subset, of course, of the total contribution from QCD. Is that true?
Yes, it's true. So yeah, that's you will always need some truncation for the higher order correlation functions. So yeah, I mean, so it's very difficult to evaluate this truncation thing. But here we think combine these two methods. Yeah, I actually want to say this. So the two methods are actually they meet with the different difficulties in practical. So in ours is what you said is about this truncation. So it's difficult to define the truncation and find so to define how big the error will be for the higher order thing. But for FRG, they're actually one loop exact. So here is one loop, and also for the higher order for 3-point correlation functions, they're also one loop exact. So we do not really have the problem to compute the 3-point correlation functions, but we have additional dimension for the renormalization scale. So that's their difficulties.
So the word identities are properly fulfilled in this scheme, I guess. So Gauge invariance is manifest.
Yeah, yeah.
Okay.
Yeah.
Don't worry. Okay. Thank you very much.
Okay, so yeah, so what I employed is basically the framework of DSE. So I just try to solve this equation. So as mentioned before, so we need the gluon propagators information and also the for this quark-gluon vertex. So basically, till now there are mainly two schemes. So one is so is the symmetry constraint quark-gluon vertex. So for example, the rainbow ladder is the leading order truncation of this quark-gluon vertex. There's also the BC Bourchieu vertex based on the wide identity. But so because of if you truncate this vertex, so generally speaking, so you lost something. So you will need to modeling the propagator and also the interaction kernel, the coupling, enhance the coupling actually to get the correct condensate, for example. But then we recently proposed a new scheme to combine the FRG data for quark-gluon vertex and gluon propagator as the input, and then we can, with no need for the interaction parameters, then we can solve this equation. Well, so basically the first truncation, because it's simpler, so we have applied this to compute the thermal properties. Here is just only for the phase diagram here, and we of course we want to proceed the computation to the thermal properties too. So the first step is the phase structure. So lattice QCD has given the solid computations at vanishing and also some smaller chemical potential based on the Taylor expansion. But due to the sign problem, it's difficult to reach large chemical potential. So functional QCD method can consistently generalize to the large chemical potential. There's basically no any problems for large chemical potential numerically. Yeah. So and also then here for the chiral symmetry for our method is very straightforward. So the symmetry breaking phases or the preserved phase are just the different solution for the quark propagator. So here the new scheme is, so as I said, so we use the FRG data in vacuum for gluon propagator and quark-gluon vertex. So this is what we have. And then for the finite temperature and chemical potential, we compute the difference Dyson-Schwinger equations. So what this equation is, we fully solve this. But for the gluon propagator DSE and also the vertex DSE, we only compute the difference between the temperature chemical potential and the vacuum. So the higher order correction is now is only the temperature and chemical potential correction. So this makes this truncation converge quickly. So with this, we can then solve the DSE for the whole temperature and chemical potential region, and then we have the quark propagator, and then we can compute the chiral condensate and also the susceptibility. So this is the plot for the susceptibility. At low chemical potential, it shows a crossover behavior, and then this susceptibility goes to divergent, so which means it goes to the critical, is closer to the critical endpoint, and then it becomes discontinuous, which means it's the first order phase transition. And this, so then we finally get this phase diagram for QCD in the temperature and chemical potential region. So first here, as I mentioned, so there will be no model parameter, the interaction parameters included for the whole curve. And so we have the consistent results for the for TC at mu equal to 0, and also the curvature is also consistent with the less QCD at low chemical potential. And then we get this CEP at around well, the temperature is 110 MeV, and then the mu B, the baryon chemical potential, is around 600 MeV. So it's also consistent with another computation from purely FRG computation. But this FRG is based as well, so it's based on the Quark-Meson model plus some gluon fluctuations. So it's a totally different resummation scheme, but we actually give the consistent predictions for the CEP. So we think that based on the functional QCD method, without considering the volume effect and also the non-equilibrium effects, so we think the QCD, the CEP is just, it should be around here. But of course, I mean, so we there are also some higher order correction for in the vertex is neglected. For example, the subleading term, the neglected dominance correction is the hadron resonance channel in the quark-gluon vertex. So we must say, I mean, our truncation till now, this new scheme, well, can work at around mu B over T equal to 4 or smaller than this. And then above this, it's because the hadron resonance channel is becoming more important. So it might be not the final definite results for the critical endpoints, but we are approaching it. And also, like, if we want to study the liquid gas transition here at very low temperature and high chemical potential, we must need this hadron resonance channel here. So this is what we want to do to include this for the higher chemical potential here. With this, after obtain this phase structure, we can then compute the QCD thermal properties, which is more related to the experiments. But the obstacle for DSCE method is that the effective potential from field theory is divergent because of the vacuum energy. So it needs to be subtracted. So here it's a mean field approximation for the effective potential of QCD. And if we put a free quark propagator here, we can see this. So these two terms basically after this integral they're divergent. Well, analytically, it's very easy to be subtracted, but if we only have the numerical computation, the non-perturbative thing, so it's very difficult to do that. So we propose a subtraction scheme based on this analytic continuation relation. So here is what we have for the numerically. So we have this, and then we interpolate the data as its integral form. So, and then subtract this term actually. Then the other terms are just as the finite term, and it should be the thermal properties as we need. And also this the other DSE groups also confirm that this scheme will lead to a cut-off independent results. So the divergence has been subtracted. So with this scheme, then we first compute the pressure, the energy, and also the entropy at 0 chemical potential. Well, so here I forgot to mention that here actually it's only for the quark part, the interacting quark. So the gluon propagator thing has been neglected here. So this is only the matter, the matter sector. So also then here actually, so it's not really the full QCD pressure. So it's only the quark pressure and also energy thing. And also here, well, we should, but here, I mean, well, so generally speaking, it still is consistent with the lattice computation for this sum of speed, but this quark part is slightly the change, the behavior is more I mean the slope is more I mean how to I mean so it's just the slope is
Steeper.
bigger, right? Yes, steeper. Yeah, thanks. Yeah, steeper. Yeah, right. So yeah, we think it's because I mean this quark sector is because the gluon part has actually slightly bigger interaction between gluons, so it makes their slope is less steeper, and ours goes to the free case more quickly. And then so we can easily generalize our computation for finite chemical potential. So this is for the pressure. Here is so when it approaches to the first order phase transition, so there will be a peak here for P over T to the 4. And then for the trace anomaly, this goes to divergent actually. And then we also compute the first order phase transition. Along this first order phase transition, we compute the latent heat. So this is for first order phase transition is finite, and then when it goes to the CEP, it's so it becomes 0. That this is also shows as consistent with the diagram of the first order phase transition thing. So with this thermal properties, we can have some we can apply them into the experiment related thing. So basically, there are these 4 applications for the QCD thermal properties. So for the heavy ion clearance, we can directly compute the fluctuations, and then it can also be measured in experiments. So after comparing with the experimental data, we can actually extract the chemical free cell parameters, and then it probably gives you some hints for the phase transition. And then also this equation states of QCD, it will be the input of the hydrodynamic simulation. So in combination with the hydrodynamic simulation, we can give more results with some more experimental data, like the particle product thing. And then for at the cosmological side, so it directly is if we study the equation of states at low temperature and high chemical potential, it directly it's related to the study of neutron star. And then here also we found well, actually here is the collaboration with the people from Bielefeld University. So we found that this can also be be extended. Our equation of state can also be extended to study the universe evolution to predict the cosmic trajectories, especially in the first order phase transition region. Okay, so here I will just introduce the studies about these fluctuations and then about this universe evolution. So first, as I said, so we have the pressure here, and then so the fluctuations can be computed by this the chemical potential derivatives of this pressure, and then so this so if this the ratio of these fluctuations can be directly extracted from the experiments. So this is a straightforward comparison with the experimental data. So here is some DSE computations based on the rainbow ladder truncation. So as of this chi3 over chi2, and here is cumulus chi4 over chi2, and this is the data from star collaboration from Rick, and so basically the DSC computation shows that the at small chemical potential, so the freeze out curve, this was the experiment actually stands for the freeze out curve. So here at low chemical potential, the freeze out curve is very close to the crossover, the phase transition line, but at high chemical potential, so generally the freeze out line is lower than the crossover line, about 10 MeV. But also here, I mean, so at low chemical potential, all the theoretical computations are consistent with the experiment data, well, mostly. But for high chemical potential, different theoretical computations give different results, and so also we cannot be really consistent with the experiment data. Here also you can see for different observables, they are slightly different from the experimental data. So here, so the next step for us is we can use the combined scheme, the functional QCD method, to compute the fluctuations for higher chemical potential, so then give a better comparison with the experimental data. And then here another thing is this to study the evolution of the universe, especially, as I said, especially for the first order phase transition. So this is related to the gravitational wave the experiments, because so usually a first order phase transition will emit great gravitational wave, but the crossover do not really enhance the gravitational wave signals. Also, this the primordial black hole product is also related to the different phase transition region. So here the evolution of universe is usually with these 5 local conservation laws. So there are 3 generations for this. So there will be 5 equations for the baryon number density, the baryon number density, and the lepton number density. So this is actually is a relation between the baryon sector and the lepton sector. So then the mechanism here is like, so if we introduce a non-zero lepton asymmetry, then it will induce the trajectory of universe evolution into also large energy, a large baryon chemical potential. So a large lepton asymmetry will possibly make the cosmological trajectory into the first order phase transition of QCD. So here is some preliminary results for this computation. So here is actually for the small chemical potentials. So before we have this computation with the so this is so this one curve is for one lepton asymmetry value, and you have this one trajectories, and this is for different lepton asymmetries. And so here, before we have this studies for even for one trajectory, we will need 3 methods separately. So for higher temperature, we use the perturbative QCD results, and then the intermediate temperature, we use the lattice data, and then here the low temperature, they use the hadron resonance gas. And if with the combined with the equation of states from functional QCD method, you can consistently, without any, you don't need to change anything, then you can consistently have this trajectory here. And also at low chemical potential, our results are actually consistent with their previous computation. And then here is the new results for some larger lepton asymmetry. So here you can see for some lepton asymmetry, for some value of the lepton asymmetry, it will induce the cosmic trajectory into the first order of its translation, and then the cosmic trajectory actually becomes discontinuous here in the first order of its translation. And here, well, I didn't really mention here. So the total lepton asymmetry. So because there are 3 generations, so there are some constraints from the cosmological experiments. So that actually, if the total lepton asymmetry cannot be so large to this first order phase translation. But if we adjust different the lepton asymmetry for different generations, it's still possible to make the cosmic evolution into the first order phase translation of QCD. And also it's anyway the first time to see how this universal evolution crossed the QCD fifth order region. So as I mentioned here, so in the future we try to in the phase structure studies, we try to introduce this hadron resonance channel, so then we can make better estimation of the CEP, and also study some information of higher order region, especially like for the nuclear liquid gas transition. So actually this nuclear liquid gas transition is probably the functional QCD method is probably the best scenario to study, because it needs the combination for the quark propagator at finite temperature and chemical potential, and it also needs the information with the hadrons. So functional QCD methods actually offer this scenario for this combined studies. And also we would like to extend the application of the equation of states of QCD combined with the hadron dynamics simulation researches, and also the universal evolution thing. Besides also the transport properties, and also the spectrum of the QCD fields in vacuum and also at finite temperature is also very interesting to study, and it can be done here with this functional QCD method. Thanks a lot.
Thanks very much. Let me clap for everyone, as is tradition these days. Are there any quick questions before I turn off the recording?
These calculations, maybe you mentioned it, but are performed in any particular gauge? Then
yeah, in Landau gauge. Yes.
You fix the Landau gauge too.
Yes. Yeah, it's the best gauge for us, because sorry.
And this is gauge invariant or not? That is the question. This scheme.
This scheme.
So anyway, so the Schwinger-Dyson
yes
scheme is a gauge invariant scheme. I never understood that. So would you obtain similar results in different gauges, or?
I know. I mean, what we have is basically the propagators. So it's not really gauge invariant quantities. So it will change for different gauge. So we apply the Landau gauge because it's a fixed point of the renormalization. So it's always QCD is equal to 0 for any kind of renormalization. So that's why we choose Landau gauge.
Okay, very good. Thank you.
Great. I was curious. So you mentioned actually you mentioned the connection to neutron stars, which is something I had read about the issues with understanding what goes on in the center of them back when we had that great event. Yeah, can you say something more about? Do you think have you talked to astrophysicists? Can they apply the calculations you've done to really understand better the insides?
For the neutron star, right?
Yes.
Yeah, I mean, so I think there are already studies about this. So basically you still use the equation of states of QCD. I mean, so all, for the hadron phase and also for the quark phase, right? So to study, like, for example, I mean, what I know is, like, for example, if there is quark matter inside the neutron star, right? So this is generally, it will relate it to the first order phase transition region of QCD. So you will need to put the hadron phase, the equation of state, and also the quark equation of state inside the equation of the neutron stars to study that. Also, I mean, so I think before that, you can, even only with the hadron phase, you can also with the equation of state, you can also, like, compute the neutron star mass or something like that. So they also predict some, like, give some constraint of the maximum neutron star mass thing based on this. Yeah.
Right. Very cool. Interesting. And in the early universe QCD phase transition, I know there've been, I think there's confusion or disagreement even just on, like, the timeline, or sorry, I guess that's really the energy scale around which this is centered. Are you in agreement with what previous groups or had found in terms of, you know, in terms of just when the QCD phase transition happens and how the entropy density will change?
Well, no, so, but I mean, I think, yeah, well, I think, like, so for example, I mean, so the main issue probably for the universe evolution is, like, it's the electroweak phase transition, right? So
Right.
probably, yeah, there, I mean, so you have some, it's a bigger signal for the possible first order phase transition thing. But here, I mean, but anyway, you will, the universe evolution will also cross the QCD phase transition.
Right.
So I mean, it's yeah, there will be some issues there in larger energy scale, but I mean, there will also be some interesting thing here in the QCD scale, right?
Right. Very cool. Let me just quickly stop the recording.